So, if you I think I put this down before, let probability. So, let me put the PMF as P of x is equal to k is our 1 over k square example, right. I think we did this earlier, 6 over pi square 1 over k square. This is for k greater than or equal to 1. So, this is also a non-negative random variable, right. So, you can use that formula. So, in this case what you get expectation of, so you have expectation of x is equal to sum over k equals 1 through infinity k times probability of x is equal to k, right, which is equal to 6 over pi squared sum over k equals 1 through infinity k times 1 over k squared, right, which is 1 over k, and this is harmonic series, right. So, this diverges to plus infinity. So, this is equal to plus infinity. So, this here is an example of a random variable with mean is equal to infinity. It is well defined, okay. It's the mean is plus infinity, the expectation of the x is plus infinity, okay. Okay. Right. Now, to move on to another example, I just want to tweak this example to make it two sided, like he was mentioning. I want to give a third example where the expectation is actually not defined, okay. So, what I am going to do is this guy has 1 over k square kind of probability mass in the positive axis, right. What I am going to do is make it symmetric, okay. So, let consider this example, let probability of x is equal to k equal to now 3 over pi squared 1 over k squared for k in all integers but not 0, okay. So, essentially this is a PMF defined over plus or minus 1 plus or minus 2 plus or minus 3 and so on, okay. It is defined over non-zero integers, okay. So, in this case, so you can verify that this is a valid PMF because I mean you can, this will sum to 1, right, this is clearly a valid PMF. Now, in this case now you have to be very careful, right, you have to compute x plus and you have to compute the x plus and x minus separately, correct. So, what you do is you will have one the expectation of x plus will be plus infinity, expectation of x minus will be plus infinity, right, because you get two harmonic series, right. And in this case what will happen is, so since they are both infinity, expectation of x will not be defined, right, expectation of x plus will have a harmonic series, expectation of x minus will also have a harmonic series, right, and therefore it will, so expectation of, so x plus will have a PMF like that, right, like 1 over k square kind of a PMF. So, expectation of x plus will be plus infinity, expectation of x minus will also be plus infinity, therefore, expectation of x will not be defined. So, what you cannot do, so one caution I want to give you is you cannot write it like this, right, the following is wrong, what I am going to write now is wrong, okay. So, you cannot write this as sum over k equals 1 through infinity k times 1 over k squared, forget the pi square outside. So, I will just do that for positive plus k equals 1 through infinity minus k over k square, right, and 3 over pi square outside, right. So, if you write it like that, you cannot cancel corresponding terms and say the expectation is 0, okay, that is not allowed, because whenever you have a summation which contains both positive and negative terms, right, you cannot take any grouping you like, right. I think you might have studied this in sequences in series, right. If you have summation a n, some terms are positive, some terms are negative, you can actually group these terms in any which, so you can get any answer by grouping the terms in some particular way, right. So, in particular you are not allowed to group such that the answer is 0, okay, that is not valid, you have to compute them separately and say infinity minus infinity is undefined, okay. You might have known that. So, I mean if you sum a n, summation a n, if the summation is absolutely convergent, then you can group any whichever way you want and you will get the same answer, but if it is not absolutely convergent, this is not absolutely convergent, you cannot group it any whichever way you want, okay. So, that is something you already know, I think. So, here the expectation is undefined, okay, it is not 0, okay, I want to make that clear, and it's and this is a different example from this. Here the mean is infinity, the expectation of x is plus infinity, here it is undefined, okay, they are different cases. So, this is not 0, you should not say this is 0, okay, this is wrong. So, this so if you say this is 0 is wrong, okay. Any questions so far?
So the Bernoulli random variable, the mean will happen as half, and there is no physical interpretation because 0 is success.
So, if you have a Bernoulli random variable is a simple random variable actually, and in that case the mean of a Bernoulli random variable with parameter p will simply be p, right. So, that is expectation of x, that is the end of it, right. So, the physical so far we have not given any interpretation of expectation of x, right. We have just called it an expected value or expectation or mean or whatever, but we have not given, it is simply the integral of x dp, that is all we have said, it is simply a number, right. The interpretation of the expectation is given by the law of large numbers, so we will give it a physical interpretation, a frequency interpretation, if a frequentist interpretation when we do law of large numbers. So, as far as you are concerned now, it is just a number, okay. Okay, everybody with me? Okay, so that concludes discrete random variables, expectation of discrete random variables. So, I have a next I will move on to expectations over different spaces. Suppose I have a situation where, so I have a random variable x, this is my omega, this is my x, and let us say I have this is g, and so I have y equals g of x. Okay. So, I have some function of a random variable which is also a random variable if g is a measurable function. So, what I want to do is, let us say I want to compute the expectation of y, expectation of g of x, right. So, what you have been so what you would expect is that, suppose I know the probability law of x here, or I know the probability law of y here, right. I should be able to compute the expectation of y in any of these spaces and they should be equal, right. So, what I am trying to say is, let us say if you have a, let us say x is discrete for the time being, just to fix ideas, if let us say x is discrete for the time being, taking values a i's. So, what I want is the following. So, I want expectation of y, right. So, I want expectation of y, right. So, expectation of y will also be a discrete random variable, right. Let us say actually let us say that it is all non negative also, to fix ideas. So, I am trying to say that I want expectation of y, I want to be able to compute as yi probability that y, see this is fine, right. Let us say I equals 1 through infinity or whatever. So, this is one way of computing it. Another way of computing it is to simply look at the value of g of x, right. I want to say it is equal to g of xi probability that x is equal to xi, right. So, I want this to be true. So, this is what I want, right. I hope this is true, rather hope, right. I say hope this is true, I equals 1 through infinity. So, g of xi probability that x is equal to xi. So, what I am saying is, so the random variable takes values x1, x2 and so on here, and it takes, after the mapping it takes values y1 equals g of x1, y2 equals g of x2 and so on, okay. So, this is something you have been doing in your elementary probability, right. So, if I tell you that these are the values that my y takes, and if you somehow figured out, say let us say I know the PMF of x, right, you can do your transformation of random variable stuff and figure out the PMF of y, and then you compute this. That is one way of doing it, and that is expectation of y. But you sometimes, if I am, so if suppose I ask you to compute expectation of x squared or log x or something, you also do a sum over x square probability. So, you know what, so you would do this, right. So, g of xi probability x is equal to xi. You probably have not thought to think whether they are actually they actually equal, right. You know that you get the same answer in any whichever way you do it, but you have just been doing it, I guess, in your elementary courses, right. Suppose my g of x is x squared, you would either compute the PMF of y equal to x square and compute its expectation, or you will simply put xi squared probability of x equal to xi, and you always get the same answer, right. It is, and so this is what you have been using, and this is what you hope is always true, right. So, that is the theorem we are going to prove in full generality now, okay. So, what I am doing here is, this is expectation over this space, if you think about it, right. I am just integrating y with respect to the probability law here, and this is integrating gx with respect to the probability law here, right. I want to say that they are all equal, right. That I just wrote it down for discrete random variables, but it is true for all random variables, okay. Understood. So, this is what I am going to prove in full generality. So, this is an important theorem. So, you have this setting, okay. So, now you have y equal to g of x, and x is a random variable on omega f p. Okay. Now, in the setting you have integral y dp is equal to integral g dp x equal to integral y dp y. Okay, that is the theorem. Okay. So, it says it has how many statements? Well, this is a definition, so that is not a statement. So, that and that, right, it says that these 3 integrals are equal, right. So, you can either compute expectation of y by just computing. So, y is the overall map, right, and obviously expectation of y is integral y dp by definition. What this theorem is saying that you can rather integrate this function g. So, if you just forget this part and you take this function g and the measure p x sitting here, you can integrate g with respect to p x, or you can integrate the function little y with respect to the law of y. Okay. So, in the more elementary terms that I just told you, this guy is equal to this, and this guy is equal to that, right, and they are both equal to expectation of y. Okay, that is what the theorem is saying. Is the statement clear? So, you are integrating over different spaces. Here you are integrating over, here you are integrating over omega, right, there is an implicit omega here. Here you are integrating over r, and the r is this r, and here also you are integrating over r, that is this r. Okay. And the measures are all different. This px is a measure here, the law of x, and py is the law of y, is a measure on this. Okay. And this is always true. So, what you have been doing is right, okay, and it holds in much greater generality. Okay. Now, how would you prove this? There is only one way to prove anything in integration, right, start with simple function, right, there is really no other way of doing it, right. Start with simple functions, then use either the supremum definition or monotone convergence theorem. Now, you have monotone convergence theorem to generalize for approximate any non-negative function using simple functions, right. So, I do not know if I will complete today. So, the time is, I have 5 more minutes, let me see if I can finish this. Let G be simple. Taking values y1, y2 dot dot yn, right. So, what I am saying is that this G is a simple function and it takes only n values, okay, y1, y2, y2, yn. Then integral y dp is equal to, so this is a simple random variable. So, I know what its expectation of y is, simply I equals 1 through n little yi probability of omega for which y of omega equal to little yi, right. So, this is my big ai, if you like, the set is my big ai, right. So, this I can write as I equals 1 through n little yi probability of omega for which g of x of omega g of x of omega equal to little y I, right. Y of omega is nothing but g of x of omega, right. So, that is my that is that, right. So, I have just written out that. Now, for the second integral, integral g dpx. So, I am looking at this function g as a function from here to here, and I am integrating with respect to the measure p x on this line, right, but g is a simple function, right, it takes values only these little y i's, is not it. So, this will be equal to sum over I equals 1 through n y I times p x of, say I am integrating with respect to p x, right. So, p x of those x's now, not omegas, right, those x's for which g of x equal to y I, right. So, good. So, that is equal to sum over I equals 1 through n y I p x of, so I can write this as p x of g inverse of y I, right, it is the same thing, right. This set is nothing but the inverse image of y I under g, right, and this is nothing but sum over I equals 1 through n y I probability of omega for which x of omega is in g inverse of y I, right. This I am again writing it out. So, I am going from measure p x to measure p, right. Now, am I done? So, this is equal to sum over I equals 1 through n little y I probability of g of x of omega. So, this is the probability of omega for which g of x of omega equal to y I, right. So, this is the same as this. So, these two are equal, right. So, we have proved it for simple functions, these integrals are equal, right. So, next what you would have to do is for any non-negative function g, you have to approximate g using simple functions from below, then use monotone convergence theorem. Okay. So, I think I am out of time now. So, we will just keep this and resume next class with the more general for non simple functions. Okay.